In this video, I'd like to talk about sample size. And for today, we're going to just do a simple calculating a sample size for a t-test. This spreadsheet happens to help you when you're doing analysis of covariance to estimate your sample size in that particular type of design. We'll see that efficiency is much better with an analysis of covariance. But for a simple t-test, we have two independent groups. And to do a t-test and to calculate the sample size, you need to know what your alpha error is. That's the p less than 0.05. You need to know what your power is. That's the probability of correctly rejecting the null hypothesis. And actually, if we go to our other little spreadsheet here, I downloaded this. So when the null hypothesis is true, the t's down here are equal to 0. When the alternative, it's effect size of 0.5, it's right here. Critical value may be right along here. Now, if the null hypothesis is true, we use this distribution. The critical value is here, and we have 2.5% of the values that are here and 2.5 that are here. That we hope our sample doesn't fall out there when the null hypothesis is true and give us the erroneous impression that our groups were different when they're really not. So that's the alpha error. But similarly, when the alternative is really true, and we have a particular critical value, and let's say it's 0.8, the power is 0.8, this beta error is 0.2, and if your t-value is too small, you won't think you found anything when you really did. It's kind of unbalanced in many ways people do it. People tend to use alpha 0.05 with a power of 0.8 because you need fewer subjects. Of course, you also have the probability of making this error here, which is, it seems, why would you, this is like you reject the, if you don't cure cancer, you find it out. But if you do have a cure for cancer, you're going to miss it 20% of the time. So, I don't know. The table is set up so that you can look at an alpha of 0.05 with the power of 0.8, power of 0.9, power of 0.95. And I guess we also do a one-tailed test. These are all two-tailed tests. And then over here, this column is effect sizes. So I've got yellow lines going where there's a guy, Jacob Cohen, in 1972 wrote a book that's just still a standard on effect size. And he said 0.2 is a small effect, 0.5 a medium, 0.8 a large. And anything larger than that, he said, basically, you don't need to do statistics to see the difference. You kind of need to do the statistics to see the difference if they're this magnitude. Tukey called doing a t-test on something that's greater than, well, some effect size out here greater than 1 or 1 something, 1.25. He called that statistical sanctification. You're doing it, but it's pretty obvious you got a difference. Here it's not so obvious. So the large is really not all that large, but it's large in this context. People have hated that there are these standards and people don't use it. We have talked about patients noticing a half standard deviation. That's purely arbitrary. That's a Hayes effect size of clinical relevance. It's not anything that's standard in the field. But that's kind of what we use, that people can notice it. It's not really a big effect, but people can notice the difference of a treatment that's 0.5 standard deviations different. So let's say you do want to have an alpha of 0.05 and a power of 0.8, and you want to be able to detect the minimally want to be able to detect an effect size of 0.5. So you need 63 subjects in each group. 63 subjects? That's a lot. That's why we do analysis of covariance, because we can take into account the correlation between the baseline and the follow-up variable value, so that if the correlation is 0.7, 0.7 squared is 49, so 50% of the variance is shared by the baseline and the follow-up. Instead of 63 subjects, you only need 32 in each group, and that's why we generally talk about sample sizes in the 30s when we can measure baseline data and then follow up. So the bigger the difference that you want to, that you're willing to look for, the smaller the sample size. And the smaller the difference you want to look for, like for example in the SVL versus PALs, they found a big significant difference because their effect size was 0.2 and they had a baseline, and they just were able to pick up a difference that was somewhat trivial. But picking, you say, well, I want to find an effect size of 0.8. Remember, God creates the effect size. You just want to be able to detect one. So making it a 0.8 and running 25 subjects in each group isn't going to give you a better chance of finding an effect size of that magnitude. So this is a simple table. It's a shortcut, and there are other more complex sample size estimates, sample size estimating programs that are freely available on the internet, and you can use those too. This is just a nice quick and dirty way of finding some simple numbers.